Hey guys, I wanted to take this opportunity to introduce myself before I come to the high school in a bit over a week and before I do the rest of these videos before that. So I'm Deepto. I'm a former Sycamore student. I'm a former student of Mr. G's, and I graduated from Sycamore in 2020, and I'm now a second year student at the University of Manchester in England, and I'm studying math and physics. So you're probably wondering, why am I doing this? Why is this happening? Why is this random, you know, former Sycamore kid coming back from college for like 3 weeks to teach a bunch of high schoolers about what, real professional physics is like? And I think that's a very good question. And I believe that if you knew me personally, it would seem very unsurprising that this is happening. This is the kind of thing I would and am going to do. And it's really because I love math and physics so much. I'm really passionate about them. In particular, I really love teaching math and physics. I think there's just something so amazing and beautiful about communicating my understanding of subjects that I really care about and think are really important to other people. And more importantly, pushing other people to deepen their understanding of those subjects. But in particular, I wanted to run this series of lectures because when I was in high school, I often felt like there was this disconnect between the type of physics that we were learning, in these AP physics classes, and the type of physics I would read about in online articles or YouTube videos. That just, it didn't match up. It felt like it was of such a different nature than, the free body diagrams and these like simple electrostatic and magnetostatic problems that we were given in MEM. Comparing that to, maybe you heard about the muon G minus 2 experiment, something that involves a really lot of complicated particle physics and quantum field theory that is just so far removed from the types of things that we learn about in high school, but is really at, the forefront of what physics today is like. And so in high school, you don't have the exposure or the resources to really understand what that type of physics is really saying. I mean, you're seniors now, so you're like 17, 18, and so you're probably 17 when you heard about the muon G minus 2 experiment. Probably most of you were like, what the hell is a muon? You These are just not the types of things you talk about in high school physics, right? And that's just the basic level. Like, what is a muon? That is the basic of trying to understand something like the muon G minus 2 experiment and phenomenon. So, as time went on, I learned more about, real physics, which is good because I'm planning to teach a bunch of lectures on them. And in order to do that, I had to go above and beyond in just finding all of these resources to learn all these things. The amount of searching online I had to do was insane. It's not just looking up random, just random questions and finding, really just easy, like mainstream, like answers on mainstream sites or anything like that. You have to find very niche websites, very niche videos, uh, to get your questions answered most of the time. Because a lot of times these topics are too difficult for like high school introductory college physics and too simple for the type of PhD level physics or research level physics that that is often published online. Those are the two types of things that you tend to see online, and in between, it's really hard to get any help on. So My personal experience was annoying, I'd say, and I'm hoping that I can contribute to your experience in making this easier. I want to give you the exposure and a bit of the resources to try and learn what is the type of physics that we use when we talk about a lot of these more complicated and relevant phenomenon that we look at in modern physics, right? So we're not necessarily going to talk about what is the physics we use to understand something like mu on g minus 2. I mean, we'll touch on it a bit at the end, but we're not going to talk about all of the complicated details with that, mostly because I don't know so much about that particular phenomenon. But we're going to talk about what are the general formalisms in physics that we use to understand how nature works, really. And in order to develop those formalisms and really do anything with them, we need to understand the math behind them. So the first part of this lecture series will talk about what is all of the math that we need to use all of these things to make them make sense, really. And so we're going to start off by learning about sets and functions, which are really our building blocks for anything that we're going to use, anything we can think of as being an element of set. And functions are really just ways of talking about associations between the different things that we're interested in. So time, position, velocity, forces, energy, all of that stuff. If we want to make connections between them, we need to talk about functions between them. And from there, we're going to talk about groups, linear algebra, calculus, and we're going to, talk about all these things in really probably more general ways than you've seen them before. Well, definitely, you haven't seen groups in linear algebra before, so that will be new. But these are all, for the most part, used to set up the frameworks for our formalisms in physics. So in particular, calculus is really not for like some sort of niche use. It's really foundational to understanding physics. It's just a part of the bedrock of it, and it's inextricably linked. And as is linear algebra, as we're going to see. And with those concepts in hand, we can really do a lot with physics then. It leads us into our study of classical physics, which is going to consist of these are not things you've heard of, probably, but we're going to talk about stuff like Lagrangian mechanics, Hamiltonian mechanics, and talk about a specific theorem in those things called Noether's theorem, which hopefully you'll see is one of the most amazing and beautiful things in classical mechanics, and it also holds in quantum mechanics, that really inspires so much of what we use in physics. Particularly, it involves conserved quantities, which hopefully you've seen from AP Physics is so important in just trying to understand a system through the quantities that are conserved, like momentum, angular momentum, charge, energy, stuff like that. And then from there, with these formalisms, we're gonna bring in a little bit more framework and talk about special relativity, which I'm you've probably heard of that one, and it may seem a bit daunting, but we're going to make sense of special relativity, and hopefully it won't seem too weird. And once we're there, we can start talking about, for one, how does physics change now in special relativity? You've probably heard about length contraction, time dilation, like time is now relative somehow in these weird ways, but we're going to see that, maybe it's not so weird and we can wrap our head around it. And then once we do that, we can start looking at what is physics like in special relativity. We can now do Lagrangian, Hamiltonian mechanics, etc. in special relativity. And then from there, we're going to get this very important example that we're going to analyze, which is electromagnetism, which hopefully you should be a bit familiar with now that you're in the midst of E&M currently. And we're going to see basically how we use Lagrangian mechanics to look at a physical theory, right? Electromagnetism has been formalized as a theory since like the 1880s or so with Maxwell. And so it's something that we know a lot about, and it's a perfect case study for Lagrangian Hamiltonian theory in applied to a physical, force of nature. So that kind of gives us a paradigm for what is a classical field theory like, and how do we understand that. And that hopefully gives you an idea of, how do physicists understand field theories in general. Because really, the stuff that we're going to do with electromagnetism is very much like what physicists do with the toy model field theories that they work with all the time. Okay. And from there on, we move into quantum mechanics. And so quantum mechanics, it's a new beast. We have to learn how to understand it a bit. It's very different from quantum mechanics. I'm sure you've heard a lot of strange things like stuff about Schrodinger's cat and just this general idea of superposition of like being in two states of one at once, and all of this sort of quantum weirdness. And we're going to try and make sense of it. We're going to kill Schrodinger's cat, so to say. Schrodinger's cat is something I'm not a fan of. If you knew me personally, if you're one of my friends, you know how much I hate Schrodinger's cat, and when people bring up Schrodinger's cat. But we will talk about that sort of stuff. We'll talk about what is quantum mechanics really saying in a sort of philosophical sense, and how do we understand what states are like in quantum mechanics. They're very different from what you would think of as states in classical mechanics, where you just have, an object or a particle moving around in space. It's nothing like that, but we're going to learn to understand it. So we'll talk about quantum dynamics. So the Schrodinger equation, it's if you've heard of it, it's on the back of my laptop, as you'll probably see when I get back to Cincinnati. We'll talk about Lie algebras, which probably sounds completely random, but we're going to see that they play once we understand what they are, you're going to see that they play a very important role in physics in general, but especially in quantum mechanics. We'll talk about specific quantum systems, especially ones that mirror classical physical systems that you're familiar with. And then hopefully at the end we can kind of get a look at what is quantum field theory like, doing a bit of basic quantum field theory, talking about what are the ways in which we use quantum field theory to talk about actual things in nature, like we've used now, or we will have used at that point, classical field theory, Lagrangian mechanics, Lagrangian field theory to talk about electromagnetism. But how do we now use our quantum theory to talk about the stuff in nature, like the forces of nature? So in particular, if you've heard about the four forces of nature, there's electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. 3 of those work pretty well with quantum field theory. The other one, for very technical reasons, does not. But in principle, we can understand all 4 of these forces through this system of quantum field theory. And I'll try and motivate what exactly that is like. And so, if you've come this far in the video, you've probably had a bit of a sense of panic because there are a lot of these new things that I've mentioned, especially for a high schooler. I think for a high schooler, this is all very daunting, given the set of things that you've learned about so far. And I want to take the pressure off. I don't expect you to come out of this series of lectures having understood everything perfectly. My greatest hope is that, even if you feel not so great in terms of your understanding of what I will have talked about for the past 3 weeks, that something maybe comes up in the next year after, 2 years after, maybe like 6 years after, and you think, hey, that's like what that kid talked about like 6 years ago. And to have some sort of light bulb where you make this amazing connection to what you're learning about, that is the most that I can hope for. I think I will be extremely happy if that happens, because that means that I actually really taught you something about what real physics, what professional physicists do, what that is like. So really, I want you to get just a basic conceptual framework of the ideas that are really important in understanding physics in its entirety. Not just, no offense to high school physics, but not just free body diagrams and just basic, really basic problems without much calculus. All that kind of stuff, because it doesn't give a real and proper picture of what physics is like. So I'm really excited to see you guys in a bit over a week. I think that, it's going to be hard. It's going to be a real learning curve for probably all of us. It's going to be for you in terms of the material, and for me in terms of trying to get through it as quickly as I would like to, because there's a lot of stuff I want to cover. But I truly think that it'll be worth it. In order to cover all I want to, I think I'll have to do a lot of videos on the math that we're going to use ahead of time. So that's kind of what this video is setting the stage for. And then hopefully that goes smoothly, and then we can move into whatever is the natural starting point once I get back to Cincinnati. So yeah, I'm really excited to see you guys, and I will see you in the next video.